Hi, I wanted to show you a demo I do with my students to get them ready for a impulse change in momentum lab that we do. And so I have a vernier force plate, and a force plate is just a force sensor, but it can measure high forces and you can stand on it. And it's connected to the computer and gives me a force versus time graph. When I stand on it, I stand still, it appears to measure my weight, but really it's measuring the normal force. And so when I jump, you'll see some interesting things happen, but we can use that graph that results to calculate the height of the jumper, at least the change in height of the center of mass of the jumper. And so we go through this analysis here. I just have it all complete. And so we'll have a force time graph. The area under that graph is the impulse, and we know it equals a change in momentum. And just before I set off to jump, my initial velocity will be 0. And so we can set that to 0. So the final velocity is just the impulse over my mass. And then we could use energy, or you could use kinematics then. You have a projectile going straight up with some initial velocity. How high does it get? Either way you do it, energy or kinematics, you get v squared over 2g. And so let's take a look at the data. And so I created a special program for this. And so to get the force plate on here, this is a digital display, and it will register the force plate reading. So when I stand on it, it's about 0 to start with. It's not a lot of newtons. If I stand still, it reads my weight. And so it's saying 900, and let's call it 68. And so 968 newtons. And notice the graph is not reading that. It started out actually with a negative value similar to that, and then is almost 0. And so I have an equation I created that I use. You might have trouble seeing this, but it's really just my little equation that tells me what the force is, and then I subtract my weight from it so that I'm getting the net force on the jumper. So this force in here, I'm not sure who that was, but they had a smaller weight. What would we say, 973. And so now when I say accept, notice the graph now is 0. And so now when I jump, the graph will be of the net force. And so I stand still, then I'm going to bend my knees, jump. And so the jump itself is pretty interesting to see. We looked at this back when we were talking about Newton's third law, that the floor can push up on your feet with a force greater than your weight. That's how you jump. And then actually here it's pushing up with a force less. So let's just display the jump part so we can see it a little better. And so here I bent my knees, I'm accelerating down, and so the net force was negative on me. The upward force of the force plate was less than my weight. So I accelerated down, and then I started to stop that, and I still have a negative acceleration, speeding up on the way down, but then I stop myself here, and so now the upward force of my of the force plate on me is greater than the weight when I cross this. And so now I have an upward acceleration, and this is an interesting shape here. It's a little more complex than usual, and we can get the area just by asking the program to do that. And so the area is 243 Newton seconds. And then my weight was 973 newtons. And so the final velocity then would be 243 over my mass, but I need to get the mass. The mass is the weight over little g. This would be newtons over newtons per kilogram. So it does give me kilograms. newtons, newton seconds, and then that is 99.3 kilograms. So my velocity is 2.45 meters per second. So the height, e squared over 2g, 2.45 squared over 2 times 9.8. And we get 0.31 meters as a record low for me, at least for today. Then I invite students to do it, and they can usually exceed a half meter. I think 0.7 something was the most that we got. So this goes pretty quickly once you get the approach down. You just have a student stand on the force scale, you get their weight in newtons, and you alter your equation so that it zeroes the force, and then they jump and you get the impulse.